All right. We are in the middle of discussing ways to strengthen a material. So ways to strengthen a material. And let's just talk about metals right now. A metal, okay. So first way is to alloy it. So what does alloy mean? It means add something else to it. And so I'm going to be discussing substitutional alloying. Substitutional alloying. What this means is that, if you remember from an earlier chapter, in order for an atom, a metal atom, to substitute for another, into another lattice and be essentially soluble, it needs to have the same crystal structure. It needs to be similar in radius. And if it's a ceramic material, there's some other requirements, but these are the two key ones for metals. And so in this case, we are talking about, and here, right, this diagram, we're talking about a pure copper material. Right here at 0, that's 100% copper. Copper is FCC. It is face-centered cubic. So is nickel, right? Nickel is also face-centered cubic. They're similar in size. One of them is bigger, one of them is smaller. It doesn't matter which one is bigger or smaller right here. But the fact that they're slightly different in radius has a huge impact on dislocation motion. Okay, so I want us to think about dislocations. And right? So in this chapter, we're thinking about ways to strengthen a metal. And so big picture, the big picture is what I really, really would like you to learn. So the big picture, we're talking a lot about plots of stress versus strain. And we know initially there's a straight line relationship. Stress, if you remember, of course, is force per unit area. Stress is equal to force per unit area. And if it's relative to the initial area, we call that engineering stress. And that's mostly what we're always going to be talking about. Engineering strain is just the change in length relative to the part's initial length. And the name of the slope of this straight line is called capital E, which is the modulus. Sometimes called the elastic modulus, often just called the modulus. And so the point is that there is an initially straight line. So this is all review I haven't begun to answer this question yet. So there, at the point at which there is deviation from linearity, okay, so you can see how it deviates from linearity, that point is called the yield strength or yield stress. They're often called, those words are just kind of, and so what we're seeing on this plot is the yield strength plotted against the amount of nickel being added. And so what we are hopefully appreciating is that, if that yield strength for pure copper is right down here at 70, okay, megapascals, once we add 10% nickel, guess what? We've got a yield strength of 100, right? So if that's 70, let's estimate that as being 100. So in other words, if we add nickel to this material, we've increased the yield strength. We've increased the linear portion of the curve, and therefore we can use this alloy with 10% nickel in an elastic way. And remember, as engineers, we don't want to go in the plastic deformation part of the curve, because when plastic deformation begins to occur, the part is permanently changing shape. So whatever part it is permanently bent at that point, or permanently longer, or permanently like messed up. So we have increased the yield strength by alloying. That's the effect of alloying. Okay, we've increased the yield strength, the length, if you will, of the linear portion. All right, now I will start to answer the question. Let me do some erasure here. All right, so what is this question asking? This question is asking, complete the curve, right? So 60% nickel, 70% nickel, 80% nickel, 90% nickel, 100% nickel, or 0% copper. What does this red line look like in this in-between area? Like what is that line doing? Okay, and we did this in class, and it was interesting because many people, there were two basic guesses, and so I don't want you to guess about this. I want you to think about it. So where I'd like you to think about it is from the perspective of being pure nickel. Pure nickel is going to have a yield strength, right? Remember the yield strength, right? Is stress, strain, linear portion, right? And it's going to deviate from linearity at the yield strength. That's the yield strength right there, okay? So pure nickel will have some sort of yield strength. And then when we add stuff to it, when we alloy it, we're going to be increasing its yield strength, right? So if we added 10% copper or 20% copper, we'd have a higher yield strength with like a, right? So as we, on the pure nickel side of things, as we add copper, we're going to be increasing the yield strength. And so from the copper side, we need to start from a point where where these two curves are going to meet. So I hope that makes you imagine that there's going to be a maximum kind of, I don't know where the maximum is. It might not be at exactly 50%, but there will be a maximum. Then there will be a decrease to some other yield strength. And I don't know what value that is. It could be here, it could be here, it could be here, it could be here, but it's definitely going to be below that point, right? It's not going to be up here. It's not going to be up here or up here or up here or here. Because, so I'm going to just draw in a reasonable answer. So there's a reasonable answer, and this would be the yield strength of 100% nickel. And so to kind of recap the concept here, when we, this is the concept, it's captured in this picture. Okay, so the pure material, let me just change color. Any pure material, right, it's going to have a linear region. If it's able to substitutionally alloy, those atoms are going to substitute in the face-centered cubic lattice in this case. And those atoms, so, well, I guess I should finish this explanation. So anyway, those atoms, because they're a slightly different size, distort the lattice. Let me just kind of write this out. So here's the why. Okay, so because the alloying ingredient is a different size, and I'm referring to the radius of the atom or the diameter of the atom, it distorts the crystal lattice of either pure copper or pure nickel. Either way, once we begin to add something else, it distorts the lattice. This slows down dislocation motion, which is called slip. It slows dislocations down. This is why alloying strengthens a metal. All right, let's end it here.